Hi, my name is Meaghan Caron, and I'm from the Bangor High School STEM Academy. For my project, I looked at Fallopian japonica as an alternative fuel source to remediate the spread of invasive species. So, being from Maine, we experience some extreme temperatures, especially during the winter, which has popularized the use of fuel sources such as wood pellets for heating homes. Wood pellets are a clean and efficient source of energy, and they can be made from an incredibly versatile set of materials. So, with this in mind, how can biomass wood pellets solve both the energy and invasive plant crisis? Well, Fallopian japonica is an invasive plant which has been the cause of many environmental and economic disturbances. I first noticed it in my own backyard, but it has spread rapidly across our country and across the world. With its vast abundance and stocky bamboo-like appearance, it may be perfectly suitable for use towards wood pellets. So to achieve this, I developed an at-home process for making wood pellets, which involved taking the Japanese knotweed and drying and blending it to a sufficient size and moisture content. Then this biomass I then compressed into a cutting board mold with and without a vegetable oil additive at various temperatures in the oven. At the industrial scale, the addition of a vegetable oil or oil additive is not necessary for the binding of pellets because there's natural materials in the wood at this scale that act as the binding agents, such as lignin and cellulose. However, dealing with less than 10 or 20 pounds of material and at this smaller scale, as I was doing, there is a requirement for a vegetable oil additive. And for me, my most successful batch constituted 1 teaspoon of vegetable oil, and these pellets, along with the dry Japanese knotweed biomass, were replicated for quality testing of ash, moisture content, and calorific value. So this dry biomass represents the unmanipulated Japanese knotweed without that vegetable oil additive. And in comparison to my bio pellets, we see that there's about 25% greater ash content and 8.5% less moisture among the pellets compared to the dry biomass alone. And this can be explained by my pellet making process and their exposure to high heat in the oven, as the 300-degree temperature may have added to the overall ash content by burning biomass in the process, as well as reducing the moisture in the process. However, this is something to be tested at a larger scale. When we look at ash content there among both the bio pellets and the dry biomass, we see that these values are noticeably higher than current pellet samples, which may average less than 1% ash. This could be due to insufficient amounts in the testing process. I used a thermogravimetric analyzer to measure these ash content values, and it works by setting time and temperature parameters where temperature is increased and ash is measured over this time period. But if there's an insufficient amount of material, the biomass can burn too quickly, rendering inaccurate readings. So again, something to be tested on a larger scale. But in a comparison of calorific value, there were 5 additional measurements taken for the calorific value of commercial pellets to obtain a sampling distribution and a 95% confidence interval for the mean calorific value of commercial pellets, which would give us a rough idea of the variability we see in these BTU measurements, as well as the variability we might see in the BTU measurements for Japanese knotweed. And with this added variability, we see that even the bio pellets perform significantly better in their BTU per pound, lying around 12,000 BTU, whereas the commercial pellets and dry biomass seem to overlap with the added variability at around 8,000 BTU. And this indicates that even without a vegetable oil additive and manipulation towards pellets, the dry Japanese knotweed biomass may have the same energy potential as currently industrially produced pellets and is extremely promising for its potential as an alternative fuel source, especially when replicated at the larger scale. Thank you, and I'd be happy to answer any questions.
Okay, I'm gonna open it up to the judges.
Okay, I've got a quick question.
Yep.
Concerning the pellets that you compared it to, what are the present composition of the commercial pellets today that you're comparing it to?
Yep, so the question was, what's the current composition of the pellets that I'm comparing it to at the commercial scale? And that's a great question. So pellets can be made from hardwood and softwood materials, and these pellets are actually a combination of both of those. So in general, for softwood, you tend to get a higher BTU, but these pellets were ones that are made at the University of Maine and are just leftovers from scraps of sawdust and wood materials that they use. So these are all recycled materials, and it's an unknown combination of hard to softwood. But it gives a true idea of the pellet itself at the industrial scale and what it acts like, what it looks like. and they're made in an actual pellet mill. So that's really what I wanted to get from those commercial pellets, is an idea that the actual pellet making process renders these low moisture content compact pellets, and how does that compare to my pellets? But something to look at in the future would be just getting hardwood pellets or softwood pellets, or a specific pellet type where I could specifically compare that to Japanese knotweed. However, the composition of these commercial pellets is truly unknown in terms of the hardwood to softwood ratio.
Okay, thank you. As a segue to that, what do you envision the scale-up process then to look like?
Yeah, so the question is, what do I envision the scale-up process to look like? And so essentially, I wanted to do that in this project, but I couldn't get lab access. But with the access to an industrial pellet mill, I could get more of this Japanese knotweed. I think the problem is not getting enough of the knotweed. I think I can harvest that pretty easily. But it's just in terms of actually going to a hammer mill, hammering that down to the compact product, and then putting it through that pellet mill. So this might be about 20 pounds of material that I need. But I think in terms of harvesting that, once I get a pellet mill, I can test this much easier and do that larger scale.
Great, thank you.
I've got a question. Were you going to go, Ann?
No, go ahead.
That buds off of that. So you said, Meaghan, you can get it pretty easily. If I was Home Depot and I came and I was like, hey, Meaghan, I'd like, I don't know, 500 tons of Japanese knotweed so we can start selling wood pellets to people. How would you scale that up? What do you think it would look like to actually build a supply for it? How would somebody collect that much?
Right. So the question is really, how are we going to collect that much knotweed? And so my goal here is not to replace the entire pellet industry. I don't want to say that this is better than all pellets that we currently have, and therefore we should get enough wood pellets in order to replace that and have everybody start using Japanese knotweed pellets, but rather to use the Japanese knotweed that we have that's already a problem and put it towards good use, because that's really the main goal, is to put this invasive plant towards good use and use it towards an alternative fuel source. So whether that renders like 500 pounds of material, I'm not sure, but we can evidently get all of the materials that we have. And the Japanese knotweed is located all across Bangor, all across the state of Maine. And I think that would accumulate enough to get a generous amount of wood pellets that might not be something to be manufactured on a huge scale and across like Home Depot all over the place, but like the cooperative extension at UMaine does with purple loosestrife. I think that we could do a similar thing with the Japanese knotweed and use what we have locally and across the state, maybe across the country, in order to create an industry for the pellets and create pellets that can be used in people's homes.
So that was a great presentation, Meaghan. Can you hear me?
Yes, thank you so much.
Yeah, and great answers to your questions. And my question was similar to that, you know, if it's illegal to grow this in the wild. So I like your answer about using what's available for sure. What about the cost? Do you see any difference in the cost to producing this versus the wood pellets?
Yeah, so the question is really about the cost and whether this will be more expensive or less expensive than current pellets. And I think when you compare it to the harvesting process of normal trees, it's not going to be a difference in cost in terms of harvesting, because cutting down this difference in terms of how much money we're going to spend. But in the actual manufacturing process, a huge part of what I want to do is make this on the industrial scale to eliminate that use of vegetable oil, because if it turns out that vegetable oil needs to be an additive, that's going to add to the overall cost. As much as I hope that that will not be the case, because really at the industrial scale, you always see the elimination of oil additives and everything but heat to make these pellets. So I think that's going to be a key component to matching the economic process that we see in current pellets, because really you want that energy output, which we're getting, but I also want it to be like economically stable, which is what we have for commercial pellets. So I think it's promising as long as we can eliminate that vegetable oil additive, and it's not going to be overly expensive or more expensive than the current process. But again, I want to test it at that industrial scale to ensure that that's going to be the case.
Yeah, great answer. Thank you.
Yeah, thank you.
Okay, it is actually 10:45. Thank you so much, Meaghan. This was marvelous.
All right, thank you so much.
We will